Hello everyone, welcome to week 7. It is our last week. This is it. So next week, just like with the seniors, you guys are going to have next week to make up whatever you have to make up, get yourself all caught up, and then that last week is exam week, and that's just going to be returning. If you borrowed laptops, you got to return laptops. Textbooks, please, if you have my textbooks, you know, make sure you get those back to the school the following week. There should be some information coming out on that, and I'll pass on any more that I gather. But yeah, let's go ahead and get started then. We got two major topics today. We want to talk about limits, specifically as they're approaching infinity with rational functions is what our goal is going to be today. I kind of skipped over just approaching infinity, and I'll explain it in this video really quick because it's not super hard. And then the next lesson is going to be on logarithms, specifically on natural logs, so that we can address that before you go into calculus next year if that is where you are headed. All right, so page 40, we're talking about limits of rational functions. Like I said, let me take a quick aside here before we even get into these notes. Something that I felt like it was going to be too busy, so I didn't put it in here. If you want to write this somewhere, you can. But it's talking about the limit as x approaches infinity. And let's use just like x cubed minus x squared plus 10, right? This shouldn't be too hard for us because if you think about it, like it is a well-behaved function, but infinity is not a real number, right? But if we plug infinity in and think what's going to happen, really our goal is to focus on this first term. When we plug infinity in, what's happening? And what we're thinking about is actually the end behaviors, right? Because if I plug infinity in here, well, infinity to the third power is bigger than everything here. So that tells us that what's going to happen is it's going to approach infinity. Think again about end behaviors, right? End behavior here, we'd say, because it's positive, we expect it to go up on the right-hand side. But because it's odd for its power, we expect it to do the opposite on the left-hand side. And if you think about what happens when you plug infinity in there, infinity to the third power is infinity. Infinity to the second power is really not relevant because this third power is so big that it cancels out the second power. Even though it's infinity and they're technically the same number, it cancels it out. And then the plus 10 is so insignificant compared to infinity that it doesn't affect anything. So we know it's going to go to infinity. Whereas we think of the limit as x approaches negative infinity, well, then you have negative infinity to the third power. And again, we're going to disregard everything else over here because it doesn't matter. It's smaller than the cubed, and the infinity in that cubed space is going to overpower it. Well, a negative to the third power stays negative, so the answer would be negative infinity, which is what we expect. As we go all the way to the left on our graph, we're approaching negative infinity. So just think about end behavior to help you with those questions. I think the homework, maybe the first 6 are like that. Just think about the end behaviors. If you know the end behavior, you know the limit. So talking about rational functions then, it's important to know the following things when determining rational functions. And that important thing is this: the limit as x approaches infinity of 1 over x, of a standard parent function of a rational function. If I plug 1 over infinity, if I plug infinity into that, well, think about that fraction of things. Like 1 out of 2 is half. And 1 out of 4, well, now you're only getting a quarter. But 1 out of 10, you're getting like a smaller piece, right? And then 1 out of 100 is getting really small. And then 1 out of 1,000 is even, and 1 out of 1,000,000 is so stinking tiny, you're not going to be able to see it. And 1 out of infinity, it basically doesn't, like, it's basically nothing. If you have an infinite number of things and you take one tiny piece of that, that's nothing. So it's important to know that whenever we have the limit as x is approaching infinity of 1 over x, well, that becomes 0, because 1 out of an infinite number of things is so infinitesimally small that it's just 0. So we use 0 to represent that. So here's what we're going to look at. We're going to actually jump to example 1 now. So example 1 says this: find the limit of, as x is approaching negative infinity, of the rational function 6x squared plus 2x over 2x cubed plus 3x. Now this looks a little bit different than that other one, right? It was really simple because it was just 1 over x. We're going to manipulate this equation a little bit to make it look nice and pretty like the other one. What we're going to do is we're going to take the numerator and the denominator and put some space underneath them. And you're going to always look at the denominator and choose the highest power in the denominator. In this case, the highest power in the denominator is x cubed. So you're going to divide every single term by x cubed. So I'm going to put over x cubed here, over x cubed here, over x cubed here, over x cubed here. And because the way we purposely did this, we know that this term right here this is always going to simplify to just a number. So let's go ahead and just simplify everything here then. So 6x squared over x cubed. Well, there's 2 x's on top to cancel 2 of the x's on the bottom. So the 6 is going to stay, and I'm going to have 1 x left over on the bottom. I have my plus sign. Here I've got 1 x on top and 3 x's on the bottom, so I'm going to cancel out one of the x's. So I'm left with 2 x's on the bottom, or x squared on the bottom, and the 2 stays on top. On my denominator, like I said, this x cubed and x cubed are going to perfectly cancel with each other because they have the same power. So I have 2, and I'm just going to keep it as a fraction, 2 over 1. And then last, I've got plus 3 over x cubed. Can't simplify anything there, so I'm going to put x cubed still. Well, now what we can think about is what is the limit as x is approaching negative infinity. So I can plug in negative infinity now. So I have 6 over negative infinity plus 2 over negative infinity squared over 2 over 1 plus 3 over negative infinity cubed. Well, any of these things that are over infinity are 0 because 6 out of an infinite number of things is just 0. 2 out of an infinite number of things is still 0. 3 out of an infinite number of things is 0. So I end up with 0 plus 0 over 2 plus 0. Well, simplifying that, I get 0 over 2, which is just 0. So the limit as x is approaching negative infinity of this expression is 0. So putting this up so you can look at it a little bit clearer. I put the directions on what I did. We divide the numerator and the denominator by the highest power of the denominator, and this is where we got. All right, let's look at example 2. What happens if the limit is approaching infinity of 5x to the 4th over x squared plus 2? Well, again, we're going to do the same thing. We're going to put some space underneath all of our terms. And the highest power in the denominator is 2. So we're going to divide everything by x squared. Okay? So I go up top and look at my simplification. Well, since there's 4 x's on top and 2 x's on the bottom, I'm going to cancel out 2 of them, and I end up with 5x squared. And again, I'm going to leave it as a fraction, so I'll just put 1 on the bottom. Down here, the x squared and x squared can cancel, so I'll put 1 over 1. And down here, I can't cancel anything, so I end up with 2 over x squared. Again, when I plug in infinity, think about what's going to happen, right? This 5x squared, well, if you take 5 and multiply it by infinity, you get infinity, right? Anything times infinity is infinity, so I got infinity on the top. In the denominator, I've got 1 plus, well, 2 over infinity is going to be 0, so 0. So I get infinity over 1, which we know just is going to be then infinity. It doesn't matter what you divide infinity by, you always get infinity. Even if you divide it by 5, it's still infinity. Infinity divided by 100 is still infinity. The only time you have to worry about is if it's infinity divided by infinity. So, come back over here then. There it is, in all its beautifulness. All right, the last example we're going to look at is 3. The limit as x approaches infinity of 2x minus 7 over 8x plus 1. Again, we're going to give ourselves some space underneath each term. Divide by the highest power. Well, the highest power in the denominator is just 1x. So I'm going to divide everything by x. So in the numerator, the 2x over x, well, the x's are going to cancel, so I end up with 2 over 1. And over here, I've got minus 7 over x. I can't do anything with it. In the bottom, my x's are going to cancel as well, so I have 8 over 1. And here I've got 1 over x. So when I plug infinity, I end up with 2 minus 0 over 8 plus 0. Again, when I plug infinity to a denominator, 7 over infinity or 1 over infinity becomes 0. And that simplifies to 2 over 8, which is 1/4. So the limit here is 1/4. Come on over here then again. There it is, 1/4. So you can pause it there and copy it. There are 3 important rules that come from that you're going to notice. I'm going to go back and show them to you in just a second. But there are 3 important rules we need to take away from there. Whenever you have f of x equaling the rational function where g of x is on top and h of x is on the bottom, I just use generic function notation. That could be any function on the top or any polynomial on the top and bottoms. If the top has a degree less than the bottom, the limit is 0. So if the numerator's degree is less than the degree of the denominator, the limit is 0. Take a look at example 1. Notice how the degree on top was 2 and the degree on the bottom was 3. Since the degree on top was smaller, the limit is 0 when we approach infinity or negative infinity. It doesn't matter. It's going to be 0. When the limit approaches negative infinity or positive infinity of g of x over h of x, and the power on top, the degree on top is bigger, well, then the limit is going to be positive or negative infinity, respectively. If you're approaching infinity, the limit is positive infinity. If you're approaching negative infinity, the limit is negative infinity. So whenever the power on the top is bigger, you go to negative or positive infinity based off whatever you're approaching. Take a look at the one we did. Notice here that the power on top was 4 and the power on the bottom was 2, so the power on top was bigger. Since we're approaching positive infinity, the answer was positive infinity. If we did this limit as we're approaching negative infinity, the answer would be negative infinity. And the last one, whenever they have the same power, whenever the power on top is equal to the power on the bottom, we use the leading coefficients to determine what the limit is. If you take a look at example 3, they both had a power of 1. Well, the leading coefficients of those powers is 2 and 8. So jump all the way to the end. 2 divided by 8, simplified to 1 over 4. That's your answer. So if you remember those 3 rules, these are super easy. If the power on the bottom is bigger, it's 0. If the power on the top is bigger, it's positive or negative infinity, depending on what you're approaching. And if the powers are the same, you take the leading coefficients of the highest powered terms and put those into a fraction. And that's it. That's how you find those limits. We're approaching infinity. So as always, let me know if you have any questions, and good luck.